In this problem, let's consider two blocks, mass 1 and mass 2, the latter of which is sitting on an inclined plane. The two masses are attached to each other with a massless string over a massless pulley, also known as an Atwood machine. In this situation, the acceleration of the blocks will be 0. In other words, the system is in equilibrium. Now hopefully this is already triggering the thought for you that the net force on the system is also equal to 0. If we know that the mass of block 2 is 10 kilograms and that the angle of incline is 41 degrees, then we can calculate the mass of block 1. In fact, another way of thinking about this system is as a rudimentary scale, using an object of known mass to determine an unknown mass of a second object. The critical step in determining the solution relies on the realization that since the block is stationary, the acceleration is 0. Which in turn means that the net force must also be 0. Let's continue by drawing a free body diagram for block 1. There's a force of gravity pulling block 1 down, and there's the tension force from the string pulling up. Now since we have already determined that the system is in equilibrium, we know that Ft must equal the opposite of Fg1. Thus, if we can determine the tension force acting on mass 1, we would also know the magnitude of the gravitational force, which would enable us to easily calculate the mass of block 1 according to the relationship Fg1 equals m1 times g. Notice now that in this case the tension force is not specific only to block 1. In a system such as this, we can apply the Bob-Marley rule. One string, one tension. The tension describes an internal force happening within the string. It also describes the forces that the rope exerts on the blocks at both ends. Since there is only one string now, there is also only one tension. Side note, the Bob-Marley rule is an unofficial designation. All of this is to say that if we can find the tension force holding up block 2, then we will also know the tension force holding up block 1. At this point, we'll need to consider the inclined plane. There's a problem-solving trick that exists to help whenever you need to calculate for an object on an inclined plane. Take a standard XY coordinate system and rotate it so that x lines up with the inclined plane. Notice the rotation of the coordinate system is equivalent to the angle of incline. So now positive y, positive x, negative y, and negative x. Since I'm interested in the tension acting in the negative x direction, it will be important to consider the other forces acting on this block. The normal force lines up with our identified positive y-axis, and the force of gravity continues to act down on the object. Since we have rotated the coordinate system, it will be useful to consider the force of gravity according to its x and y components, while recalling that the system's 41-degree rotation is equivalent to the difference between the original negative y and the current negative y. As a reminder, our system remains at equilibrium, which means that the tension force in the negative x direction is equal in magnitude to the force in the positive x direction, and the only force acting on block 2 in the positive x direction is the x component of Fg2. Now we have a right triangle here with a hypotenuse equal to Fg2, and we are trying to find the side opposite the 41-degree angle. So the force of gravity in the x direction equals Fg2 sine 41 degrees. Recalling our earlier work, we can now conclude that Fg1, which is equivalent to negative Ft, is also equivalent to Fg2 sine 41 degrees. Substituting for gravitational forces, we have m1g equals m2g sine 41. The g's cancel on both sides. m1 equals m2 sine 41 degrees. And substituting in the mass of block 2 leaves us with m1 equal to 10 kilograms times sine 41 degrees, giving us block 1's mass, 6.56 kilograms.